So good morning, everyone. So today I'll be touching upon many different pieces of work carried out with a number of collaborators that you see here on the first slide. So especially in this room, because we study, mathematics of deep learning, I'm sure everybody can appreciate that data, algorithms, and architecture all interact and play a role in affecting generalization in deep learning. And as a community, we've been working hard to build theories that would kind of bring all these different aspects together to provide a good theory for understanding generalization in deep learning. But whenever you think that we have such a theory, various cracks appear. So one particular crack that I'll be focusing on today is memorization. And memorization is really hard to actually model theoretically and doesn't seem to be too easily compatible with good generalization. So let's look at some prior work showing that deep neural networks do indeed memorize. So for example, a quick Google search on data reconstruction from neural networks gave me this paper that was published at NeurIPS last year, where the authors showed that they can reconstruct training data from trained neural networks. So in particular, in the top row here, you see some of the images that were reconstructed from the model. And on the bottom, you see the nearest neighbors that actually appeared in the training set. And you can see that these images are actually incredibly close. On the language model side, a group from Google, led by Karolina, showed that one can type in a partial prompt for a particular paragraph, and networks can reconstruct the rest of the sequence of the tokens of pretty high precision. That's especially true when the models get larger. The same group with a number of other collaborators also showed that one can actually extract even personal identifiable information from trained models. So neural networks do memorize their training data. We've seen plenty of evidence in practice. But what does this really mean for generalization? So this is really what I'll be focusing on in this talk. Now, what is memorization in the first place? What is its role in generalization? Is it benign, useful, or maybe perhaps it's even necessary in some cases? And then at the end of the talk, I'll also discuss some strategies how we can potentially mitigate some forms of memorization. Okay, so I'll start with reviewing what is memorization, how people define it in the literature. By the way, if there are any questions for the talk, feel free to raise your hand, interrupt, and so on. So many different formal and less formal definitions exist. So I kind of divided them up into a few different categories. So the first category is reconstruction-based. So here we are trying to reconstruct training inputs, either partial or whole images, or perhaps pieces of text by interacting with the model. And on the more formal side, this can be captured using various information-theoretic measures and looking how many bits maybe are stored about the training data in the weights. A different category is leave-k-out-based definitions of memorization. So here we are comparing a model that trained on all the data and one that trained by excluding a particular data point. And for example, Feldman in his work in 2020 then defined memorization of a particular example by looking at probability of predicting correct class for the example of interest, let's say Z, by comparing how differently these models behave in terms of their predicted probability of the correct class. And yet another category is membership-based. So here, the goal is to predict whether examples were in the training set. So here we have membership inference attacks. Some of them, in fact, actually use leave-k-out-based estimators. And we have information-theoretic measures again, but now that ones that condition on so-called supersample. So they're trying to infer membership of what from this larger set actually was or was not in the training set. And I'll come back to this particular notion later on in the talk. We'll be using it in our work.
A question?
Yes.
Is it completely obvious that if you remove Z, you have a decrease in accuracy for the red model?
It's not completely obvious, and it depends on the example. So you could think maybe the most obvious example is something like, let's say, passwords, right, or some personal identifiable information. Then, of course, to generate. So here's, of course, in terms of classification models, but the same extends to generative models. But of course, you wouldn't expect the model to generate this secret kind of weird random, string.
I see. So mem z can be negative.
Sorry?
Mem z can be negative.
Yeah, maybe I put it on backwards then. I don't know, probability of correct class, yeah, it should be higher, the example was included. So it shouldn't be negative. Right, you would expect the model, if I leave this example out, I'm less likely to generate either correct label or complete the sequence of tokens. Right, so it shouldn't be negative actually. Okay, so of course, memorization and learning have been studied in the past and for quite a while. So let me review some of the basic facts. So first of all, of course, excessive memorization and generalization are in fact compatible. And here we have a very simple example of one nearest neighbor. We know that one nearest neighbor converges to 2 times base risk. So generalization and memorization can exist together. Now, one way to mitigate memorization is for differential privacy. But we know that learning with DP comes at a very steep cost, and sample complexity scales very poorly with dimension. That's something just as a side note, if you're familiar with unlearning, so where the goal is to remove the influence of some of the training data from the trained model, very commonly it's approached using DP, but I think this also, kind of the cost of privacy also motivates unlearning approaches that avoid differential privacy. And finally, we know that high average generalization error also implies memorization. So generalization error is defined as a difference between test and training errors. And if generalization error is not on the order of 1 square root of n, then we know from from information-theoretic generalization bounds that there is a growing amount of information about the training data in the learn predictor.
Can I just ask, sorry, just to help me think about it? Because I'm always confused. I think you're going to address this about like where memorization ends and where generalization begins. There are some tasks which are kind of like, I just want you to retrieve the right answer.
Yes.
So in some sense, it's kind of like I'm asking the model to memorize. Then it's hard to tell between that and very uncommon examples where there's kind of nothing to do.
Yeah. Yeah.
And maybe you'll just address it later, but I don't know how to think about it.
Yeah, so I don't think I exactly addressed it, to be honest. And as I said, there are many definitions of memorization, right? So now it depends kind of what is your task, right? If your task is to literally recall exact, regenerate, for example, inputs, then, memorization is not problematic. On the other hand, it's literally memorization is overlapping with good generalization, right? So I think it really depends on how you define your task, and to compare it to how generalization and memorization should interact. So I can't quite answer that question, but I think for the examples that I'll be looking at, memorization can or cannot be harmful, and it's something I'll touch upon for good generalization. But I'm not considering tasks where my goal is to actually recall or completely reconstruct some of the training inputs. That makes sense.
I see, that does. Yeah, I don't think the question was totally reasonable. So,
Well, it's a reasonable question, but as I said, I think it kind of it's task dependent in that sense, right? But I'm really talking about kind of standard scenarios, I guess, and where you want to generalize on unknown data distribution, right? Kind of, standard setting. And now, also, when you think about, let's say, nearest neighbors, you do literally have to memorize to even predict on new and seen examples, right? So again, generalization and memorization can live in harmony with each other. Okay, so all of these examples are really not about deep learning. Now, how about deep learning? What happens there? So in the famous paper by Zhang et al. In 2017, the authors show that neural networks trained by stochastic gradient descent can memorize randomized labels. So here, stochastic gradient descent is used to train a network on examples where the label was flipped randomly. And we see that the networks actually achieve, again, perfect performance. So they totally interpolate these randomized label data. And of course, that means that the network had to memorize. So stochastic gradient descent is not limiting model capacity. models can be trained for zero error, even with stochastic gradient descent, and are therefore capable of memorization. So, whatever implicit regularization stories we can tell about stochastic gradient descent, it wouldn't really be about this limiting model capacity in terms of interpolation. And also, generalization actually remains good under non-trivial memorization. Now, my red box got shifted a little bit, but even when label corruption is high, meaning that, for example, so on the x-axis it shows what percentage of examples had randomized labels, we see that the test error is actually still fairly low. So the takeaway is that generalization and memorization, again, can happen simultaneously, also in deep learning. So the work by Zhang et al. Led to a number of theoretical investigations. And some of the key ones that I'll mention here were, for example, due to Bartlett et al., showing that benign overfitting is possible in overparameterized linear regression. This work has been also extended in shallow neural networks. And we also show in our 2020 paper with Negri and Roy that despite these interpolating predictors not having good generalization, or even if we cannot show good generalization of these interpolating predictors using uniform convergence approaches, we can study related predictors, ones that we call surrogate predictors, that do generalize due to uniform convergence for as long as we relate these surrogates to your original predictor. So that's like a very hand-wavy argument, but again, we show that benign overfitting is possible and interpolation is possible and compatible with generalization. Now, can we generalize without memorization? Seems like a natural question because every time we do see neural networks, again, we kind of do see memorization. So I would say one of the first pieces of work to look at this was by Feldman in 2020, showing that learning may require memorization. So Feldman constructs a family of long-tail data distributions and proves that memorization is actually necessary on average for achieving close to optimal generalization. And more recently, we've looked into this in the setting of stochastic convex optimization, and we linked, again, optimal learning and memorization. So we showed that memorization is actually necessary in high-dimensional stochastic convex optimization. So I'll be looking into this work in more detail in the next few slides, but really what this says is memorization can actually be necessary.
Sorry, can I ask a question?
Yes.
So earlier you mentioned that memorization and generalization can happen simultaneously. I wonder whether throughout the course of learning, memorization comes first and then generalization, or do you mean that they both happen simultaneously, even during training?
Yeah, that's a good question. So here we study predictors that we actually learn, so the algorithm outputs at the end, not looking at the training trajectory. But I do remember some pieces of work. Unfortunately, I don't remember who it was by, but looking how memorization may be necessarily at early steps of training because you don't really know what is generalization and what information you should be keeping. Again, in some simplified setting, I don't quite remember the details, but there is other work looking into this, which I think is very interesting too.
Really interesting to see a phase transition from memorization to generalization.
Yeah, and I think like all the work around grokking also kind of, aims to look at that as well. Okay, so why study stochastic convex optimization? Well, first of all, it's well studied. We know that optimal learning rates in this setting and what algorithms achieve these rates. It's also rich enough to exhibit actually many of the deep learning phenomena. For example, banana overfitting that I mentioned a few slides back. Also, algorithms matter here. If we consider arbitrary empirical risk minimizers, they require actually the number of samples that scale with the number of parameters, while stochastic gradient descent requires number of samples independent of dimension. The goal in stochastic convex optimization is to minimize risk, which of course depends on the unknown data distribution, and is equal to the expected risk of some predictor theta, where the z denotes the labeled example, f is some loss function. In particular, of course, in stochastic convex optimization, we consider it to be convex for fixed labeled example z. So some examples of this, can be logistic regression, support vector machines, and so on. Okay, so how should we evaluate a predictor? So let's review the steps of learning. We first pick a data distribution D, which produces a training set Sn. And then we apply an algorithm of our choice, which produces a predictor theta. The excess error, so the predictors will be evaluated under excess error, which is defined as the risk for your learned predictor theta hat minus the best predictor in the class that you're learning over. Now, of course, the second term here compares to the nature, which knows the data distribution, right? We're allowing it to know the data distribution, and we're picking the best predictor. So the question that we ask in this setting is, what is the minimum information that a learning algorithm must retain from its training set to achieve small excess error? Okay, so what do we mean by memorization, and what do we mean by information? So I'll review that in the next few slides. So what we mean by memorization, so again, let's look back at the same setting. We have the data distribution, which generates training inputs, apply the algorithm, learn a predictor. Now, assume that the data distribution actually generates a second sample, which we'll call the go sample. We flip a fair coin n times, producing a sequence of UIs, valued 0, 1, and we set example Z star to be either coming from the actual training set or from the go sample, depending on the value of UI. Now, we'll consider an adversary whose job is to guess whether a particular example Z star came from the training set or not. And the adversary is, the attacker is allowed to know the data distribution, the predictor that we've learned, and of course, it gets the sample Z star. So we see that an adversary is alpha sound if it has no more than alpha probability of a mistake for each go sample when predicting membership. So it cannot always predict membership, and it has to be accurate enough. And we see that an adversary certifies a recall of M examples if with constant probability it identifies M training data when fed in N training data. So that's exactly what we'll be trying to capture. What is the recall? What recall can the adversary certify for our sample? Yes?
So I know that you mentioned differential privacy towards the training. This sort of looks very similar to how you would define differential privacy.
That's right. It does look similar. So you'll see that we'll be working in a higher dimensional space relative to the number of examples we have, where DP guarantees would be not interesting anymore. So you'll see that in the actual theorem statement in a few slides. But yeah, you could use DP now to guarantee no memorization, which has a very similar setup as you see here, really to identify whether something came from the training set or not. Okay, so if such an adversary exists, we say that the learning algorithm memorizes M samples because it can tell for M samples, at least M samples, whether they came from the training set or not. Okay, is this clear? What do we mean by memorization? Okay.
What are the conditions on this adversary?
So on the adversary, conditions are what it's allowed to consume, which is the data distribution, learn predictor, and the sample that you're giving it, which I'll be actually changing in a few slides a little bit. And also in the theorem statement, you will see that we pick alpha for the alpha sound condition, but then we'll be kind of proving its certification rate.
But I mean, you're requiring abstract existence without additional conditions.
Yeah, so in the actual, so this is just really the definition of the adversary. Now, its existence will be proven in a particular condition. So we'll be constructing a particular example, which actually don't go into details, but it's really a mean estimation problem. So for this particular problem, we'll be constructing a data distribution such that an adversary that certifies particular recall exists. Okay, so the key result in the paper is memorization can be necessary, and it says the following. So fixed alpha, which was alpha for the soundness of the adversary. Then there exists a d-dimensional stochastic convex optimization problem with a convex one Lipschitz loss and an alpha sound efficient adversary, such that for every learning algorithm that achieves epsilon excess error with n samples and dimension that is relatively large compared to the number of samples, there exists a data distribution D such that the adversary certifies a recall of and order at least 1 over epsilon squared samples. So there are 2 things that I highlighted here. One is dimensionality dependence. Note that this is near optimal. And as per question a few minutes back, we can learn privately when the dimension is smaller. Therefore, of course, ensuring that there is no memorization. Yes?
Sorry, question on the definition, like to identify M data point, you mean like with certain probability, you only care about M data point being identified. Does it have to be like the same M data point that's getting identified with some probability?
No, it's just like if I supplied n samples, where n was a training set size, then I just need to identify at least m of those with high probability. What do you mean by this? Maybe I'm misunderstanding your question.
Sorry, I just wanted to understand the definition, because like I was thinking of like with certain probability, you mean like with a high probability, you only care about like m data point being identified every time, or do you care about like the same data point really being memorized?
Oh, whether the same data point? No, I don't think so, if I understand your question correctly. Yeah.
So the definition is that adversary gets n samples, and the prior probability for each one is 1/2, right? It's randomly either from the training or from the other side. And
from the ghost,
it needs to return m
correctly identified.
So all of them have to be correct. What?
No, I give n examples. And so the way we construct the adversary has a particular decision rule that it depends, like it in the mean estimation problem, it basically looks like it uses the kind of fingerprinting lemmas from DP world, and it let me think how to explain it. Can you repeat your question?
So the question is, what is the rule for the adversary for the certify of a recall? So what adversary, what should the adversary return? Should it point out to m samples out of n and say that these come from the...
It doesn't get all the n samples at the same time. It gets 1 sample at a time. And it's being given training samples only, really.
Okay, so what is the certificate?
So the certificate is that if I keep feeding it n samples that actually train, it makes no more than m mistake, or n minus 1 mistakes, I guess.
You can show the definition again.
So it doesn't get the full sequence, if that's what your question is.
So can I ask maybe like a related question? Just so what happens to the adversary that always says, yes, this was from my training data set? In the sense that these, it's like 50-50 chance, so it'd be like...
Yeah, so it cannot, it wouldn't satisfy the soundness condition.
Well, so I see, so you need alpha to be like bounded away from a half. That's what you're saying.
Basically, yeah.
I see, but it could recall examples.
Say it again?
It could recall roughly n over 2.
Yes. Oh, could recall...
I mean, if like each one is just in there 50-50 and it just says yes to everything, not like half.
Yeah, so... but we give the recall rate, right? We say exactly that the recall rate should be the order at least 1 over epsilon squared. So it's not about half or not half, if that's what your point is.
Oh, so is it like of the n samples you presented, it gets n over epsilon squared is m, or is m 1 over epsilon squared?
There is a correspondence between also the sample complexity here and how many samples it recalls. So in this particular problem, and I think I maybe said here, that every sample efficient learner memorizes a constant fraction of its data. That's really the kind of consequence of this. Because this recall rate that we get here in the theorem, 1 over epsilon squared, matches the minimax sample complexity.
Got it. I see, that's the recall rate, not the total number of things it recalls.
Yeah, sure.
No, I understand. I was not understanding that.
Yeah. So I'm still not sure if I solved the previous confusion, but I'm also not entirely sure what the question is. Sorry.
Boris was asking about alpha. I mean, you can pick any alpha you would like.
Yes. So here you can pick any alpha you like. It's
So maybe omega should exclude 0. But yeah.
Got it. Okay, I think I understand better.
okay. I'll keep going. Okay, the buildings are messed up again. Okay, so let me connect this kind of notion of memorization to information. So there is a notion of conditional mutual information introduced by Steinke and Zakintano in 2020, where they measure the dependence between the training data and the learned model, just like a usual information-theoretic measures. So the way it works is the following. First, we sample some supersample Z. So kind of similarly as before, you can think about it as the ghost and the training set, but basically just twice the size of your intended training set. You'll sample a membership vector uniformly over 0, 1. So again, each entry will now determine which of these samples from the supersample are actually in the training set. So the training set is constructed by taking the supersample and the membership vector. And CMI then of an algorithm measures mutual information between the output of your algorithm and this membership vector conditioned on the supersample. So of course, the setup is very similar now as before, right? So maybe I'll stick with this slide. But I think kind of similar to your question before, where what information the adversary is allowed to consume, whether it gets an entire training set or not, or maybe that wasn't the question.
I was trying to understand the definition. Yeah.
What?
I was trying to understand the definition on that slide.
Okay, we can maybe
yeah,
chat after.
That was part of that.
Yeah, so you can see the connections because now really given the entire supersample, we need to identify what was in the training set or not instead of just one example, Z star. And if you kind of decompose CMI in terms of entropy and use Fanos inequality on the second term, you'll see that the existence of an adversary that can identify which examples were in the training set or not, so the membership, U effectively, also yields a lower bound on CMI. Okay, so what does this mean, and what is the point of looking at information-theoretic terms here? So CMI can also bound generalization. We know that expected generalization error is bounded by CMI, the algorithm, divided by n square root of that. Now, if CMI is lower bounded with this 1 over epsilon squared, then we can actually show that it cannot be used to prove generalization of these epsilon learners. So if we rewrite the excess error, upper bounded in terms of just the difference between training error and minimum training error, so the optimization error, plus generalization error, which is the yellow term. And since we know that CMI is of the order of 1 over epsilon squared, at least 1 over epsilon squared, then this whole bound will be actually, if we select this n to be the order of sample complexity, we'll actually get the expected generalization errors of the order of 1 at least. And looking back at the excess error bound, which we know excess error had to be bounded by epsilon since we were looking at epsilon learners, we see that we get a vacuous guarantee. So what this really says is that CMI framework cannot be used to study generalization of these optimal learners in stochastic convex optimization setting. Okay. So the take-home message is really that sometimes memorization is necessary for learning. Yes?
2 questions. Sorry, it's probably quite basic. How important is the stochastic part of your convex optimization? Can this equally hold just for non-stochastic? And second question.
So it is important for studying all of these kind of information-theoretic quantities as well. So let me think about. mean, it's the same importance as in the privacy world, right? But I'm not sure if I have a good one-sentence answer. So maybe there are privacy experts here who can answer better. Or Dan, do you have a good answer?
Well, I didn't quite understand the question. What stochasticity are you referring to?
In the optimizer, I guess, could you not just run GD? And
Well, the stochastic and stochastic convex optimization is not about the optimizer. It's about the data.
Okay, maybe I just misunderstood that. Okay.
Okay, so sometimes memorization is necessary for learning. But not all memorization is good for generalization. So for the rest of the talk, yes?
Yeah. Just a question, why not just consider, maybe it leads to a different picture, like memorization to just be like a small deviation from perfect interpolation of training data set, Like saying the training error is less than epsilon.
Yeah.
And when epsilon is equal to 0, essentially, at least for supervised, then you're memorizing the label of each sample. And so if, how does this relate to this?
If you're interpolating the training data.
Yes.
So what's the exact question? Sorry. If you're...
So for example, if you define memorization to be training error less than epsilon.
If you define memorization as a training error being small.
Being small.
Okay, well, that wouldn't work, right?
Mm-hmm.
Because, for several reasons. It's not really an issue unless you're, let's say in the random label training case, that may be a good definition, because if you memorize random label examples, then of course it's problematic if you achieve 0 training error, right? You had to memorize. But in this case, it's not an issue because you can have epsilon learners where the generalization error should be converging. And so it's not really, it would be overlapping with generalization completely, that makes sense, right? So that's the definition of generalization. You have to generalize for these optimal learners, right? Their empirical risk and risk will be converging to 0. Does that make sense? Yeah. Okay. Okay, so not all memorization. Okay, so take-home message was sometimes memorization is necessary for learning, but not all memorization is good for generalization. So for the remainder of the talk, which I think I don't have too much time left, I was planning to review some of the empirical work looking at kind of when memorization is good or not. Yes?
Sorry again, very quick. So this maybe is hopelessly naive, but is there some idea that there's some kind of memorization term you can almost add onto your classic generalization bound, which in some sense changes your training error? Normally you have a training, kind of empirical risk plus some complexity term. There's this idea that you can measure some kind of memorization of your model that you've learned, and you use that to somehow adjust the generalization bound. Is that kind of the idea, or is that
I think I get your idea. You're saying, is there a different decomposition such that we would be just looking, okay, here's a generalization term, here's memorization term, but we don't really care maybe for as long as this other part converges. And that's an interesting question. I haven't thought about it. I'm not sure I can answer, but yeah, it's very interesting proposal.
If I understand this correctly, then
Yeah.
bounds of this kind exist, where basically they take into account the empirical error and they shrink effectively the complexity of the class.
Say it again?
So if I understand correctly the question, then these kind of bounds exist.
Okay.
But they take into account the empirical error of the predictor.
Yes.
And effectively, they shrink the complexity.
So I guess I don't quite get it just looking at excess error, for example, in terms of adding and subtracting training error, because I don't see how it would solve the
So
issue.
basically, these kind of bounds, they don't upper bound the deviation of the empirical from the expected error.
Okay.
But they scale this with a relative.
Okay, I see. So basically, it would be eliminating maybe the minimum training error term and studying a slightly different bound, which only looks at the risks effectively, or maybe it's a discussion to be had after, but I would be curious to see that work. And Okay. So looking at the empirical work, I wanted to return to my data diet work that asks what examples should we be training on. So here we proposed a very simple score for measuring examples' influence on generalization. It's kind of a very, again, simple way of looking at training, just looking over a single training step. And we see that just based on the statistics early in training, we can actually order examples from, increasing score, and actually find examples that are more important for training. So we order the examples, we take the highest score examples, which will also turn out to be the highest influence examples. So we only train on the top S% of examples and remove the bottom scoring examples. And what we see is the following. So here, the dashed line shows performance when training on all the data. The red line, which is dropping off quickly, shows when we randomly select what examples to train on. So on the right-hand side, we train on almost all examples, 90%. And as we go from right to left on the x-axis, we are training on a smaller and smaller fraction of examples. So we see performance drops off quickly. But if we use this particular score that I mentioned in the previous slide to select what examples to train on, we'll see that performance actually remains really good. So this is the blue line until, like pruning 50% of examples. So we can select only 50% of the training data and still have very good performance. And only it drops off later on. Now, what is the role of these high scoring examples? So we looked at it by kind of varying what examples we select with an offset. So offset on the left-hand side would be 0, meaning that we train on these kind of small scoring examples. And on the right-hand side, we would be training again on the high scoring examples. And we see that, indeed the score kind of represents or pretty accurately captures what examples are important for generalization, but there is something funny going on here at the end. And actually excluding some of the high scoring examples boosted performance. So let's look at these examples kind of in more detail. So here on the top, we visualize low scoring examples, on the bottom, high scoring examples. And what we see is that low scoring examples are kind of very easy and typical. Bird is obviously a bird here. And the high scoring examples, they are actually more difficult. Their labels are ambiguous. For example, here we have now a parrot that's sitting on a truck. So there could be multiple labels assigned to this. So can we take this difficulty to the extreme? We randomly select 10% of examples and reassign their labels to a wrong label and train a network that interpolates the training data, again, indicating memorization, because you can only learn these examples by memorizing them. So we see that of these randomized examples now, they were kind of, the blue was the distribution of their score prior to changing the labels, and the orange was after changing the labels, and we see that they shifted from easy to hard. So in other words, really kind of these high scoring examples turn out also to be kind of difficult and outliers, and ones that actually have to be memorized. And if we do the same experiment with the offset, we see now that excluding some of the high scoring examples gives you a huge boost in generalization. Of course, unsurprisingly, because they are now the ones that we memorized. So maybe kind of to summarize the key learnings here, the most difficult examples tend to be memorized and have high influence on generalization. And whether this influence is positive or negative, it really depends on the nature of the data that we have. If the influence is negative, removing these examples and therefore avoiding their memorization may improve generalization. So while we saw that memorization may be necessary for good generalization, of course not all memorization is good. So a similar message comes from our pruning work, where we see that underfitting some examples, again, may improve generalization. So what is pruning? What I mean by pruning is shrinking model size by removing some unimportant connections of the network. Now, what are important? It's usually the goal is to preserve the function, and there are many algorithms proposed out there on how to kind of, heuristics for how to identify these unimportant connections. And what we often track in these pruning algorithms and how well they perform is we track just top-line metrics like accuracy, without really deeper understanding what examples are being affected, for example. So now the folklore around pruning is that it should be decreasing model capacity. But we also know that once model, or not know, but kind of what's believed really, and this is a quote from the double descent paper, once model complexity is sufficiently large to interpolate, and meaning that achieve zero training error, then increasing complexity only decreases test error. Following modern intuition of bigger models are better. But what we see in pruning actually goes against this. So we see that pruning the model, which is the blue line here, can actually boost performance. So here, the kind of relative dense model performance is just this flat line. And we see that in the highlighted region, the prune model actually performs better. So bigger models may not necessarily be better. But what is really happening here? So again, if we looked at classical explanations, they say that pruning reduces overfitting. Now, but is that really what's going on? So what we find is that underfitting story is complex. Well-performing pruning techniques do regularize, but actually in a data-dependent way. So it doesn't affect all examples in the same way. And generalization differences come from pruning algorithms having longer training times, actually, and maybe actually interpolating some of the training data better. But once you start pruning, some regularization kicks in, depending on how many parameters you're dropping. And we find that this regularization is data-dependent, because the sparsity masks that we select are actually also, of course, data-dependent. We don't just randomly select what to prune, but we select based on gradients, weights, and weight sizes, and so on. So I think I'm pretty much out of time, so I'll skip some of these plots. But really, kind of the takeaway is similar to the data diet work that I mentioned previously, that pruning can actually induce a data-dependent regularization and reduce memorization as a result, and improve generalization, again, for certain data sets. Okay, so some memorization is needed for good generalization, as we saw from Feldman's work and from our work, at least, of course, if you fix various other things like HGD, training with stochastic gradient descent, fix architectures, data we deal with, and so on. But not all memorization is good. So this is really coming from this empirical work. Asking, of course, for no memorization may be too much. Perhaps we can ask for less. So again, I kind of want to stop here and maybe just go to the questions, right? Because I think 11:05 was...
We started a little bit late, so you can definitely have at least 7 more minutes if you want. So I don't think we're...
Okay, so I'll maybe quickly review kind of these proposals. To what extent can we control memorization without hurting generalization? So as I said, maybe we cannot get rid of memorization completely, but maybe we can have better control over it. So one, of course, approach would be to employing differential privacy. It's well studied. It requires a very simple adjustment to the training run. We know limitations of differential privacy methods. And we also know, though, that it affects performance, right? So if we, do a lot of DP, right, we know that models don't perform well, at least in the pre-training stage. So we need tons of data to maintain performance and use differential privacy. A different approach could be controlling unwanted memorization by controlling the example frequency in the training set. So again, this could come from data curation methods and so on. And so let's look maybe at this one quickly. So there was work, again, by Karolina et al. On quantifying memorization across neural language models, where they show that the higher the repetitions in the training set of these, I think pieces of text in this case, the higher fraction of this piece of text was extractable from the model. So kind of, it seems like a simple way to control unwanted memorization would be by controlling example frequency in the training set. A second approach could be applying unlearning to mitigate memorization. So I mentioned unlearning briefly previously, but really here we have, a standard training procedure, and that produces a learned model. And we may receive some requests to remove the influence of some data, which we'll call the forget set, from the learned model in an efficient way while preserving good performance. And we want that model to be similar to one that never trained on the forget set. So trained on the rest of the training data, but by leaving the forget set out. And here we would be asking, how close are these models? Now, there are many approximate and learning techniques there. As I said, one approach is, of course, differential privacy, but it comes with its own disadvantages. There are many kind of local updates that one can do to unlearn, but unlearning is not equally effective for all examples. So, again, maybe I won't go into too much detail here, but the key takeaway is that it depends on how many times your examples were repeated during training. It depends how easy the examples were, and it affects the effectiveness, really, of these kind of approximate unlearning methods, such as, for example, doing gradient descent or fine-tuning to unlearn. Okay, so unlearning may mitigate memorization, but with some caveats. It depends on the nature of the set that we want to unlearn and how many times this data appeared during training. So maybe one thing I didn't mention from these slides that I skipped is that we also looked how whether an example is more like in distribution or an outlier affects unlearning effectiveness. Okay, so one more thing to mention is that we could consider pruning. So here, again, maybe very short, we look, before we've seen evidence that pruning introduces data-dependent regularization and classification. How about in large language models? How does pruning affect different capabilities? So there are two key capabilities, fact recall and in-context learning. So some of this was mentioned, of course, in the previous talk, so hopefully people are quite familiar with this. But with fact recall, you can really think about, we train on some training data and we expect that information maybe to be extractable based on kind of the information encoded in the weights. And for the in-context learning, the information comes in the context, and we want the model to answer questions only based on the information in the context, not really because, a particular fact, let's say, or, a linear regression predictor was stored in the weights or appeared during pre-training. So most generic tasks demand both capabilities. And in this work, we try to disentangle them and see how pruning affects each of them. So we choose a set of tasks, some of them that fall under really fact recall. So you simply ask questions that should have appeared in the training set. And on the other extreme, we have very kind of general tasks like the one mentioned again in the talk before mine. Let's say doing linear regression. And then there are things in between where maybe you override some information that existed in pre-training data and provide different information in context, or maybe provide some of the context that will be useful for answering a question. So how does pruning affect a capability? We could imagine a few different scenarios. One is if the capability is highly distributed, then perhaps as we prune the model, performance should drop off linearly. In a different world, perhaps there are some vulnerable bottlenecks. So we may preserve performance for as long as we don't prune this bottleneck part, and then performance drops off rapidly. And in a different world, we see that maybe kind of all the information was in the safe spot. So we can prune the whole bunch up until we hit this spot that stores the information. And what we see is that actually when you prune large language models, they affect these kind of fact recall tasks versus in-context tasks very, very differently. So fact recall tasks, the performance starts to deteriorate very, very quickly as we do pruning. And in context learning, we can do a whole bunch of pruning until in-context learning is actually affected. So again, maybe kind of one way to control or to mitigate memorization, unwanted memorization, could be via pruning, and which maintains in context learning capability, but gets rid of the whole bunch of facts. Now the question is really what facts are, of course, being memorized. Okay, so to summarize, memorization is not only benign, but it's also necessary in some cases. And not all memorization is good for generalization. And this is really all empirical work for the second question. So I think there are many, many interesting theoretical questions around this. And also removing memorization completely might not be a good choice, but we have various other options to mitigate it. So some of the open questions on the theoretical side, I think it would be interesting to characterize precisely the trade-off between learning and memorization and identify what to memorize, maybe to maximize generalization. Also, I think it would be interesting to understand what does this necessity for memorization mean for unlearning. I think generally unlearning really still lacks theory, and I think there's a lot to do there. And on the empirical side, I think it would be interesting to think about architectural design choices that would be best for controlling information access to certain, let's say, facts without losing performance. And again, looking at maybe various kind of heuristics for identifying what examples are likely to be memorized. So this might not be suitable for DP, but I think it's interesting for various other reasons. Okay. Thank you very much.